Alright, so in the last video I gave a little bit of introduction to this topic, and so now let's actually talk about what I'm trying to do here. So we're looking at this particular, let's see here, so this is numerical experiment. So this first one here in this paper that we're talking about, so we have utt equals uxx on this particular domain, and we give these specific initial conditions. This has an exact solution given by this formula. And you can, without too much difficulty, just use basic calc 1 to verify that this is a solution. Okay, so basically what we want to do is we want to take this and we want to implement it and see what happens. So that's what I am doing here. So this is a thing that I've written up just for my own notes so that I know how to implement such a method. And so I actually start here by giving a little bit of an introduction. Well, I don't really introduce the thing itself. I just sort of jump right into it. So we want to solve this particular problem. We have an exact solution. And so this is a system of equations that needs to hold. We need this system to hold for every single v and w in the finite element space. V and w are the test functions. And then we have the flux terms that we use. So let's see here. Okay. So for each time t, uh of t is a function of x, and it's an element of VHK. So that means for each x and for each point x comma tn, if t is the discrete time point and x is an element of ij, then we have this formula: uh of x comma tn equals the sum from L equals 0 to k of this thing. Okay. So remember, I talked about how VHK is a finite element space. So for each ij, so any function of VHK when restricted to ij is a polynomial of degree k. So this L equals 0 to k, those are the different polynomial degrees, and so we use those to refer to the basis functions. I even say that here. Phi L from L equals 0 to k is a basis for ij. This should be phi L with an exponent j here. Now these j's, I say that. Here superscripts are used for indexing rather than exponentiation. Because we need a lot of indexing here. So unfortunately we use a lot of exponents here that aren't actually exponents. They're just indices. Okay, so anyways, so we know that when restricted, at a discrete time point tn, when restricted to the interval ij, is a linear combination of basis functions. And so uln comma j are the coefficients of these basis functions, as L ranges from 0 to k. N, of course, gives you the index of the time point, and j gives you the index of the space interval. And of course, we don't have any n for phi lj. This is a basis element, but the basis functions that we use for VHK are independent of time, and so there's no n here. Okay, so these are what these functions actually look like. This is how we actually get specific values for these functions. of x comma tn, we have this formula for it. And what we're really solving for in this method is each of the uln comma j. And we solve for that for every single L from 0 to k, for every single n from 1 to however many discrete time points we have, and for j equals 1 to however many space intervals we have. And then similarly, we need to get QH, and QH is going to be written as a similar thing. This, of course, should be phi LJ. And yeah, we have to solve for the q, l, n, comma, j's. Okay, so let's see here. We had the second order leapfrog method. So basically what I did here is I just took that, if we go back here, where is it? Here. So these are the equations that we use to implement it. This UTT being approximated by this leapfrog here. Now these two equations, 41 and 42, these are written in terms of UH's and QH's. Also, they have the hat terms here. So what we want to do is we want to replace the hats with the actual fluxes that we're using, and we want to replace the UH's and QH's with those sums that we just showed. And when we do that, we get this equation. I pulled the 1 over delta t squared out of this thing. And so, of course, like for example, this is going to be UH. What exactly is this here? Yeah, so this is UH n plus 1. So you look at this UH n plus 1 that we see here, that's exactly what this, it's a little hard to write, UH n plus 1. That's exactly what this first term is here, because it's just this sum. And that's exactly from our formula from before. Okay, so these are our equations. Okay. And there is a little, you do have to be a little tricky here. Yes, these things you have to be really careful about, because these are important. Because what's happening here is, if you consider the interval j, you've got, we refer to this as xj, and this is going to be xj minus 1/2. This will be xj plus 1/2. So technically, instead of this being evaluated at j plus 1/2, this should be evaluated at xj plus 1/2, and this is xj minus 1/2, etc., etc. But it doesn't really matter. You know what I mean. Well, you know what I mean, because now I've just told you what I mean. Anyways, so this is the interval ij. You've got xj as the midpoint, and then the left endpoint is xj minus 1/2, and the right endpoint is xj plus 1/2. This is a little tricky to get used to, but you get used to it once you work with it a bunch. So anyway, so we remember we're evaluating q hat. So just looking at this term, we're evaluating q hat at xj plus 1/2. So we're at this right endpoint, and we have this minus sign here. So that means we're approaching this point from the left. And if we approach it from the left, wait. Yes, we're approaching from the left. And so that means that the actual function that we're using is the function on the interval ij. Because if you're a little bit to the left of xj plus 1/2, then you're going to be in the interval ij. So in order to evaluate this, in order to evaluate qh at xj plus 1/2 from the left, you need to evaluate qh on the interval ij. And so that's why we use qln comma j. That's why we use j here. However, when we come to the next part, here we're subtracting this term, and we're evaluating at xj minus 1/2. And so now we're looking at this term, and now we're here, and we're approaching from the left. So if we're approaching from the left, we're approaching this way. So that means the functions that we're evaluating aren't going to be in ij, they're going to be in ij minus 1. You can imagine this is going to be xj minus 1, and this will be xj minus 3/2. So right, if we're approaching xj minus 1/2 from the left, we're going to be approaching from within this interval ij minus 1. And so we have to actually evaluate QH on the interval ij minus 1. And so that's why we use this j minus 1 here. And this is one of the trickiest parts to deal with when implementing the this finite element method, is that you have to make sure you're using the information from the correct cell. Similarly, when we move down here to this part, we're evaluating it at xj plus 1/2. So again, we have this arrow here, and we're approaching from the right. So our information is coming from the cell ij plus 1. And so that's why we're evaluating UH from within the cell ij plus 1. And then here for the final term, you can check it, but you end up just using the cell ij, so it works out well. Okay, so now we have all these UL n's and j's and QL n j's that we need to solve. Okay, so if we're back up here, remember we have these v's and these w's, and this needs to hold for every v and w, where these are elements taken from the finite element space. And by the way, this holds for a particular ij, so v and w need to belong to the polynomial space pk on the interval ij. So in order for this to hold for any v and w in that space, it suffices for it to hold for all basis functions, because the basis functions are a basis for ij, for the polynomial space on ij. So therefore, we need this to hold. So basically, all we've done here is we've taken, like, anywhere you see a phi m, this used to be a v or a w, but instead we're going to make this hold for every phi m j, where m ranges from 0 to k. And so that's the only main change that we have between the previous equation and here. I also did some algebraic manipulations. I moved some things around, as you can see. Yeah. And so this is what we're going to do. And so now we have, let's see here. It's not quite clear yet, but let's see here. Yeah, I guess it's clear from this point. So if you look at this, you can actually, so like just looking at this term here, this is an integral of a sum from 0 to k of UL n plus 1 comma j, phi lj of this thing. So what you can do is you can bring that integral over ij inside, because the UL n plus 1 j's, those are just constants. The only things that really are depending on this interval ij are you're integrating phi lj times phi mj. And so what this really looks like is this is really the sum from L equals 0 to k of UL n plus 1 comma j times the integral over ij of phi lj phi mj dx. Okay, and so all these integral terms are just coefficients, and so now this is just a linear combination of the UL n plus 1 j's. And so seeing that, you can look at the rest of this and realize, wait, these are just two equations in two linear equations in the UL n plus 1 j's and the QL n's, or the UL nj's and the QL nj's. Of course, you might use different n's and you might use different j's, but these are just linear equations, and we want to solve this for each phi m where m ranges from 0 to k. So then you just do these two equations k plus 1 times, and so then you've got a system of 2 times k plus 1 equations that you want to solve for. So that's what this really comes down to now. Now we're at the point where we see that we've reduced this to a system of linear equations. And that's the whole point of numerical analysis. Is you take your PDE system, you discretize things until you can write your PD, you can write your approximation as a solution to a system of linear equations, because linear equations are easy to solve and nonlinear equations are not easy. And especially for computers, linear equations are the only things that they can do. So anyway, so we have linear equations here. And so what's really important is we want to look at the exponents here. So what do these things depend on? So here we're solving, in the first equation, we're solving for ul n plus 1j. We're solving for those terms, and that depends on the ul nj's, the ul n minus 1, ul n minus 1j's, and the ql nj's, and the ql nj minus 1. So that's the first equation, and then the second equation, we're solving for ql nj, and the only thing this depends on are the ul nj's. And of course, the j just tells you about spatial information. So what you can do is, so here, I think I described this here. So suppose that for a fixed time Tn, for any m less than or equal to n, we know the values of ul mj and ql mj for all l and j. So then you use the first equation to compute ul n plus 1j for all l and j. And then you solve for ql n plus 1j using all of the ul n plus 1j's which you have already computed. So now we have an inductive process. If you know all of the ul nj's and ql nj's, if you know all of those values for a certain n, then you can get them for n plus 1. And now you set up an inductive process. So that's the inductive step. The only thing that's remaining then is the initial conditions, or the first step. So the thing is that if you look here, uln plus j depends on the ul nj's and the ul n minus 1j's. So you need to go back to discrete time points. Therefore, the first two discrete time points you need to figure out yourself. And so the paper describes how we find the first two time points. But the basic idea is that for the first time point, you can just do the L2 projection. You take, because you're given the initial function, here the initial function is just, what is it? The initial condition is the function u at time 0 is sine of pi times x. So you're given that initial function, and you just project that into the finite element space, and you do that using L2 projection, which means that you find a function. Okay, did I explain that here? I don't know if I did. Right. So so let's say what's here? What do I call it? UH0. By the way, I'm writing this here. This is not related to anything around it. So UH0 satisfies the integral of UH0 times V dx is going to be equal to the integral of, what was it, sine pi x V dx for all V in the finite element space, VHK. And the way that you solve for UH0 here, I think I talk about that later, actually. Let me just double check here. Yeah, that's just this right here. Okay, so I'll talk about this later. But yeah, use the L2 projection. But then, So then what you have to worry about is you have to worry about that second time point. And so what you have to do is you have to do something tricky to make sure that you're getting a close enough approximation. So what we do is you take u and you write it as a Taylor. You just use the Taylor expansion of u of xt at t equals 0, and you evaluate at delta t to get this formula for u of x comma delta t. It's just this infinite sum that you see here. And then basically, let's see here. So I'm pretty honest here. I forget how to forget how many terms you need to use to get a particular level of accuracy. I think I just say, okay, so for k equals 3, so let's see here. I believe that using a second order leapfrog method will yield fourth order accuracy in time. Okay, so second order leapfrog method, I'm pretty sure gives you fourth order accuracy in time. So, yeah, basically you just need to, so this sum from n equals 0 to infinity of this thing, you need to use enough of those terms so that your accuracy is high enough to maintain the accuracy of whatever method you're using. Okay, and then what we're going to do is, so I'm pretty sure that what I end up doing, yeah, okay, so I do the sum from n equals 0 to k plus 1. So I'm pretty sure if you do it to k plus 1, then you'll get at least k plus 1 order accuracy for this particular time step. And that's supposed to be the accuracy that you get overall, as you can read in the paper. And so this should suffice. And so here's what you do. Oh, well, this is an interesting point. I wonder if this is why... I do get some slightly different numbers when I run the program versus what the paper gets. And I still get the correct order of accuracy, but that's only when I'm using k equals 1. So maybe I'm using either too many or too few terms in this approximation, but in this Taylor approximation, but whatever. Anyways, what you have to do is you have to take the sum from n equals 0 to k plus 1 of delta t to the n over n factorial, blah, blah, blah. You got to figure out some way to get a hold of this. And so you have to do some... So let's see here. You have to do some tricky things. So what you have to do is you can't use time derivatives here. That's the issue. The issue is this formula, you've got the sum and you've got time derivatives of u. But we don't have time derivative information. We only have spatial derivative information. At least for time 0. We only have spatial derivative. Of course we don't have time derivative information because we don't have any other time points. So what we do is we break the sum up into the odd and even values of n. And then for some of these you're going to have just for some of these you have you're taking the time derivative an odd number of times, and sometimes you're taking an even number. Now if you're taking an even number of time derivatives, that's okay, because we know that u satisfies utt equals uxx. And so if we can see, like over here, what we're doing, of course we throw out n equals 0, that's not important because then you're not taking derivative. But if we look at over here, UH0, so we know at any space point, at any point in time, you can take, or at any point at all, you can take two derivatives in space, or you can take two derivatives in time, and that ends up being the exact same as two derivatives in space. So here, if you're doing an even number of time derivatives, then you just do for each pair of time derivatives, you can turn that into a pair of space derivatives. And then you're able to actually evaluate that because you're able to take space derivatives of UH0 because you already have this function for all points in space. Now for odd n, it's a little different. Basically what you have to do is you have to break off all the even derivatives that you're taking, and then you also have this final derivative with respect to time that's left off by itself, and you have to take that time derivative of UH0. But we know, actually, if we're told that the time derivative of UH0 is precisely the projection of V0. Right. Yeah, this is like one of the initial conditions that were given. It's explained earlier in the paper. And so this is something that we can also get our hands on because we know what UH sub t, because PHV0 is given to us already. And in fact, in this particular problem, the time derivative of UH at x0 is 0. So this isn't even something that's incorporated into this particular problem because it just drops out. But anyways, you see at the end here, everything is in terms of stuff we know. We either have we don't have any time derivatives. Everything else is things that we know and spatial derivatives of things that we know. And so we can compute this. Okay. And now we're actually going to get a little bit more into the gritty details of how this code implements it. So all of the stuff that we've done previous to this gives you okay, you just choose a polynomial basis and then you're able to implement it. But now we're actually going to choose a polynomial basis and show you what the linear equations look like. And because of the length of this video, I'm going to stop here and pick this up next time. And so yeah, we are getting close to being able to actually code up this problem.